Welcome to our 10th video in which we collect climate data and model this data with a periodic function. Here's the process. I went to weatherbase.com and I searched for my city, Edinburgh in Scotland. I've got the monthly temperature averages here. We can see evidence of a periodic behavior here. By the end of the year, we're back at the same temperature. And in the middle of the year, we have a nice warm summer. And if you think about it, weather patterns are periodic. Otherwise, we wouldn't know what to expect in the summer. It'd just be random. The data on the website was in a horizontal format, so I had to put it in a vertical format in order to put it in the TI-Nspire. And remember, in the TI-Nspire, you need to give a title for the variables, otherwise it doesn't know how to operate. So I opened a new page. It plots the data, but we have to tell it which variable goes on each axis. And we've done that before. I put the month on the horizontal axis, and then on the vertical axis, the average temperature. And we get this shape. So the question is, how could we fit a periodic function to that data? Well, to begin with, we'll calculate the parameter A using this formula. So the maximum value of the temperature was 15.1. So I can do 15.1 minus the minimum temperature, which is 3.9, divided by 2, gives me 5.6 for the value of A. Similarly, 15.1 plus 3.9 over 2 gives me 9.5. That's the value of D, using this formula here. Now we can calculate B as well. We can say B is 360 degrees divided by the period, which is 12. And that gives B is 30. I just chose degrees because my calculator was set up in degrees. Okay, so now we found B, which is 30. And then the value of C we'll come to later. That takes a bit of time. So right now we're going to leave C as 0 and see what the graph looks like. So here we have the values we've found for A, B and D. And a quick visual check seems to show the amplitude looks reasonable. The the principal axis looks reasonable at 9.5, and the period looks reasonable as well. But of course, it's not in the right position. We have a horizontal translation to effect. And just roughly looking at this, we've got 3 months here, we've got 8 months there. It looks like a horizontal shift of approximately 5. Okay. So working that out does take a bit of time. So we know the value of A, we know the value of B, we know the value of D. We need to find the value of C. Okay. Well, I just picked one random point right here. And that will give us the value of X, which is 5, and the value of Y, which is 10.5. So then we know everything, we just have to solve the equation to find c. So if I replace those values, I get y is 10.6, and then I get 5.6 sine 30, x is 5 minus c, plus d, which is 9.5. And you basically have to rearrange that equation to find c, which takes a few steps. So first step, 1.1, is 5.6 sine 30, 5 minus c. And then dividing by 5.6, 1.1 divided by 5.6. So 30, 5 minus c is sine inverse 1.1 over 5.6. Notice I'm not using the calculator yet because that would build up errors. Now, have I got room for the final step? Just about. So 5 minus c is 1 over 30 sine inverse 1.1 over 5.6. In other words, let's put it here. C equals 5 minus 1 over 30 sine inverse 1.1 over 5.6. Now if you work that out to three significant figures, you'll get C is approximately 4.62. So remember we said it would be roughly 5? Well, now we've worked it out. Now this is the procedure to find C. We could have used any point here and we would have got a slightly different value of C. That's mathematical modelling. It's not exact science. Well, let's see what happens with our 4.62. When I put that here for the value of C, you can see the graph has moved into a much more representative area. It seems to be representing the temperature really well here, and then not so well here. But if you think about it critically, well, who says the temperature data has to follow a sine graph exactly? Maybe it won't. It's a model. It's not a mathematical proof. When I put in 2 years, I can see, you know, a sort of a reasonable fit over the 2 years. It turns out we can tweak it a little bit. Looking at this critically, I think if I move it to the left by a half, maybe it will fit better. So I did that. This affects a horizontal translation to the left of 1/2 month, then it fits a lot better. Part of mathematical modelling is tweaking the model to try and make it fit as best you can. And thanks to the wonderful TI Nspire, you can put a photograph in the background. Here's my beautiful city of Edinburgh, basking in the summer sun. And did you know in Edinburgh they have the world's biggest arts festival every summer? Here's my son busking in the in the Royal Mile in Edinburgh. Thanks for watching.